morning viewers, today we are going to discuss linear transformation. This lecture includes the definition, we will give some examples of linear transformation, then we will discuss some important results regarding this, and then we will introduce the concept of rank and nullity, and finally some results related to rank and nullity. To start with, I will first give the definition of linear transformation. For this, let us consider two real vector spaces V and W. A linear transformation T from V into W is a function, I say T is from V to W, which assigns a unique vector T alpha in W for each alpha in V such that it satisfies the properties. The first property is that T is additive. By this I mean to say that when T is operated on alpha plus beta for each alpha and beta in V, then it will be transformed to T alpha plus T beta. By this we say that T is additive. The second property is T is homogeneous. By this I mean to say that when T is applied on C alpha, alpha is a vector and C is a scalar in R, then it becomes C times T alpha. So, T C alpha is equal to C T alpha, and if these two properties are satisfied, then such a transformation T is called a linear transformation. I introduce the principle of superposition. By this I mean to say that if I have two vectors alpha beta in V, then T of A alpha plus B beta is equal to A of T alpha plus B of T beta, where A and B are scalars in R. The way I have defined this transformation, I can say that T from V to V into W is a mapping such that T of C alpha plus beta is equal to C times T alpha plus T beta for alpha beta in V. In fact, this will become an alternative definition for linear transformation. So, instead of satisfying two properties, linear property and homogeneous property, the two properties are combined into one single property defined in this manner. Now, a linear transformation from V to V is also called a linear operator on V. To illustrate what I have done, let us consider two vector spaces V and W. By this I mean to say V consists of a set of vectors, two operators, one is addition of vectors, another is scalar multiplication defined in V as well as in W, and they satisfy certain properties. So, that way V and W are two vector spaces. Then a linear transformation from V into W is denoted by TV, provided a vector in X goes to Tx in W and a vector in Y goes to Ty in W, and they satisfy the property, the homogeneous property and the linear property which I have defined earlier. Now, in this case I say V is the domain of the linear transformation, while W is codomain for the transformation. This set which consists of images of x and y in V, all x and y in V, that set is called range of TV, and definitely this is a subset of W. Later on we will prove that it may be a vector space. Now, let us take an example. We have a transformation T from R cube to R2, which is defined as T of x y z, a vector, goes to x z in R2. So, this is a vector in R3 and this is a vector in R2. So, if we define this transformation in this particular manner, then we will show that T is a linear transformation. Now, if it is a linear transformation, one has to prove that T is additive. By this I mean to say that if I take alpha and beta, two vectors in R3, then T of alpha plus beta is T of alpha plus T of beta for each alpha beta in V. So, let us consider alpha as x1 y1 z1 and beta as x2 y2 z2. So, these are two vectors in R3. Now, T of this is equal to T of this vector, because sum of two vectors is x1 plus x2, this is y1 plus y2 and z1 plus z2. So, sum of these two vectors is equal to this. So, T of this is equal to this vector. Now, this transformation says that the first component will become the first component of T alpha and the third component will become the second component. So, that way T of x1 plus x2, y1 plus y2, z1 plus z2 will become x1 plus x2 and z1 plus z2. Now, this will simplify to x1 z1 plus x2 z2, and by definition of the transformation T, x1 z1 is T of x1 y1 z1 and x2 z2 is T of x2 y2 z2, and that is how we have proved that T of alpha plus beta is equal to T of alpha plus T of beta, and that proves the additive property. Now, we prove that T is homogeneous. For this purpose, we have to show that T of C alpha is equal to C times T alpha, C being a scalar. Now, to prove this, let us consider alpha as x1 y1 z1 and the scalar C, then T of C times x1 y1 z1 is equal to T of Cx1 Cy1 Cz1. What I have done is I have taken the scalar C inside this. So, this is equal to C of x1 and C times z1. So, T of this 3-dimensional vector is this 2-dimensional vector, and from this we can take C outside, and what we have is C times x1 z1, and that means C times T of this is equal to C times this vector. That means this a vector in R3 maps to a vector in R2. So, C times T x1 y1 z1 is equal to C times x1 z1, and that proves the homogeneous property, and hence it is a linear transformation. In this, we have again defined a linear transformation from R3 to R3, and will again show that it is a linear transformation. So, the transformation is T of x y z is R times Rx, Ry and Rz. Now, to prove this, again we have to first show the linear property. So, it is C times x1 y1 z1 plus x2 y2 z2. Now, I am actually combining the two properties, the homogeneous as well as the additive property. So, I will say T of C x1 y1 z1 plus x2 y2 z2 is equal to T times C x1 plus x2 C y1 plus y2 C z1 plus z2. So, basically I have combined these two vectors in this form. Now, using the definition for the linear transformation, this expression can be simplified to R times Cx1 plus x2, R times Cy1 plus y2, R times Cz1 plus z2. That is the effect of the transformation, is that each component is R times the original value. So, this left hand side is now C times Rx1, Ry1, Rz1 plus Rx2, Ry2, Rz2. So, sum of two vectors, and that means the transformation T applied on C times first vector plus the second vector is equal to C times the transformation applied on the first vector plus transformation applied on the second vector. This proves that T is a linear transformation. Now, I will give geometrical interpretation to the examples which we have taken so far. The first example is the linear transformation T defined from R cube into R2 is T times x y z is equal to x z. We call it a projection transformation. Let us consider this vector. This is the vector, 3-dimensional vector, x, y, z, this is x axis, y axis, z axis, this is the x component, this is the y component, and this is the z component. Now, when this vector, when we consider t of this vector, then what we have is xz. So, what is xz? This is x and this is y. So, this is the vector which is the projection of this vector. So, this transformation means that this vector is projected, this vector has a projection this. So, when we apply linear transformation on this vector, what we get is this projected vector. So, in the second example, we consider the vector alpha in R3 as x, y, z. This is the vector x, y, z. It has three components, x, y and z. Now, when we apply linear transformation on it, then it becomes Rx. So, Rx is, this is Rx, this is Ry and this is Rz. So, each of these is R times these values. So, Rx, Ry, Rz are these components, and then the vector will be this vector. So, this vector will be transformed to this vector, and what we have seen that this vector is rotated to this vector when we apply this linear transformation, and that is why we call this transformation as rotation. Now, in the process, if r is less than 1, it is a positive number lying between 0 and 1, then we say that this is contraction, and when r is greater than 1, we say it is dilation. Then in the next example, t of x1, y1, z1 is equal to 2x1, y1 plus 1, and the third component is 3z1. So, the transformation from R3 to R3, this transformation is not a linear transformation. So, what we have to do is that this linear property is not satisfied for this transformation. So, let us consider t applied on c times first vector plus second vector in the domain set, domain vector space. So, it is t times cx1 plus x2 if I combine the two. Second component is cy1 plus y2 and cz1 plus z2. Now, when t is operated on this vector, then according to this definition, the first component is 2 times this. So, it is 2 times cx1 plus x2. The second component will map to y1 plus 1. So, cy1 plus y2 becomes cy1 plus y2 plus 1, and the third component cz1 plus z2 will become 3 times this component. So, cz1 plus z2 is 3 times cz1 plus z2. So, t of this vector is this. So, let us simplify this. So, t 2 times cx1 plus 2 times x2 is c times 2x1 plus 2x2, but when it comes to this, it is cy1 plus y2 plus 1, it is cy1 plus y1 plus 1 plus y2, cy1 plus 1 and y2, and this is c can be taken out, is 3z1 plus 3z2. So, this vector is nothing but c times t of x1, y1, z1 plus this vector, but this vector is not t of this vector because plus 1 is missing from here. So, what we can say is the linear property is not satisfied, or we can say that this is not equal to Ct of x1, y1 plus z1 plus t of x2, y2, z2. So, this transformation is not a linear transformation. Apart from these examples, there are some simple examples of linear transformation from V to VR. The first is the identity transformation, we denote it by I, such that every vector in alpha maps to itself. Since a transformation from V to V, so every vector alpha in V will map to itself. Such a transformation is identity transformation, and one can easily see that it is actually satisfy this property, like I alpha plus beta is A times I alpha plus I beta, and that means I applied on this is A alpha plus beta and I applied on this is A alpha plus beta. So, both the sides are equal and one can say that identity transformation is a linear transformation. The another simple example is the zero transformation. We denote it by theta and we define it as that theta of alpha is equal to 0. That means every alpha in this vector space V will map to theta, additive identity. So, this is a zero transformation. Also, every vector in alpha will map to 0. So, this also satisfies linear property that can be very easy to prove, and that means that it is a linear transformation. This is another example. Here we define the linear transformation T from R2 to R3, and it is defined as Tx is equal to Ax for x in R2 and Tx in R3, where A is the matrix of 3 by 2 order. So, let us define this transformation T as x and y. Any vector in R2 will map to this vector in R3. Now, we show that T is a linear transformation. Now, again the method of proof is the same. We start with C alpha plus beta and the vector C alpha plus beta in V. We operate T on this, and what we have is T times C x1 y1 plus x2 y2. It is a two-dimensional vector. So, alpha is x1 y1 and beta is x2 y2. When this is operated on T, when T is operated on this vector, then we should have T times Cx1 plus x2, Cy1 plus y2, Cz1 plus z2, and that means 1 0 1 1 0 1. This is the definition of this linear transformation, and when you multiply it is Cx1 plus x2, this multiplied by this is Cx1 plus x2 and plus Cy1 plus y2, and then this is equal to Cy1 plus y2, and then Tc alpha plus beta, one can see that this is equal to C times x1, second component is x1 plus y1 and third component is y1, and plus from here we can write down x2, this x2 plus y2 the second component, and what we have is y2. So, Tc alpha plus beta is equal to C times 1 0 1 1 0 1 x1 y1 plus 1 0 1 1 0 1 x2 y2. So, if we use that, this is actually equivalent to this, and this means that this is C times T alpha plus T beta, and that proves that it is a linear transformation. Now, we will discuss some important results in the form of theorems. Theorem 1 says that if T is a linear transformation from the vector space V into W, then the first result is that T of theta 1 is equal to theta 2, where theta 1 is identity vector in V and theta 2 is the identity vector in W. The second result says that T of alpha minus beta is equal to T alpha minus T beta. Now, the first result says that the identity vector of V under this transformation will map to identity vector of W. Now, and this says that this we have additive property. Now, this is the subtraction. Now, let us consider the proof for the first property. So, we can write down T theta 1. What is theta 1? Theta 1 is an identity vector in V. So, when identity vector is added into identity vector, what we have is identity. So, theta 1 can be written as theta 1 plus theta 1. So, T of theta 1 plus theta 1, since T is linear, becomes T theta 1 plus T theta 1, and that means T theta 1 is nothing but theta 2, because T theta 1 is equal to T theta 1 plus T theta 2 theta 1. This is possible only when T theta 1 is equal to theta 2, and this shows that the identity of V will map to identity of W. To prove the second property, we consider T of C alpha plus beta is equal to Ct beta plus T alpha, because T is a linear transformation. But what we can do is we can simply take C is equal to minus 1, and that means T of alpha minus beta is equal to T alpha minus T beta. So, proof of the second property is also simple. Now, some more results. T is a linear transformation from V into W. Then for any vector alpha 1, alpha 2, alpha n in V and the scalars C1, C2, C alpha, Cn, then T of C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is equal to C1 T alpha 1 plus C2 T alpha 2 plus Cn T alpha n. What we are going to do is, we have n vectors here, we have n scalars. What we have done is, we have taken the linear combination of the vectors alpha 1, alpha 2, alpha n and the scalars C1, C2, Cn. Now, T of this vector, now since we have V as a vector space, so if alpha 1, alpha 2, alpha n, they belong to V, so this linear combination will also belong to V. So, this is also a vector in V, and T is a linear transformation, then this T times this vector is equal to C1 T alpha 1 plus C2 T alpha 2 plus Cn T alpha n. We have, if we have only two vectors, or we can say n is equal to 2, then T of C1 alpha 1 plus C2 alpha 2 is equal to C1 T alpha 1 plus C2 T alpha 2, the superposition property. But actually these are n vectors. So, to prove this, what we can do is, we can consider C1 alpha 1 plus C2 alpha 2 plus Cn alpha n. We can take this as one vector, and we have C1 alpha 1 one vector plus another vector, linear property can be applied. So, we will have C1 T alpha 1 plus the second vector. Now, the second vector, the same thing can be applied to the second vector repeatedly, and what will have a final result, that T of C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is equal to C1 T alpha 1 plus C2 T alpha 2 plus Cn T alpha 1. So, basically a generalization of what we had earlier. So, for it is that result was for two vectors, this is for n vectors. Now, we since V is a vector space, so it will be having basis. So, let us consider S is a basis for the vector V. Then given the linear transformation T and alpha belonging to V, then T alpha will be completely determined by its images T alpha 1, T alpha 2, T alpha n. The idea is that what will happen to these vectors alpha 1, alpha 2, alpha n. So, we have this is the basis, is n dimensional vector, V is n dimensional vector space, then T alpha being the image of a vector in V, then the image vector will be determined in terms of T alpha 1, T alpha 2, T alpha n. So, let us prove this. Since S is a basis for V and alpha belongs to V, then alpha, which is a linear combination of these vectors, S being the basis, can be written as alpha is equal to C1 alpha 1 plus C2 alpha 2 plus Cn alpha n. Then, since T is a linear transformation, so T of alpha is equal to C1 T alpha 1 plus C2 T alpha 2 plus Cn T alpha n. Now, this is the result which I have just established in my last theorem. Then, T alpha is determined by T alpha 1, T alpha 2, T alpha n. How? So, see, this vector alpha is determined by the scalar C1, C2, Cn, and alpha maps this alpha 1 maps to T alpha 1, alpha 2 maps to T alpha 2, alpha n maps to T alpha n. Since C1, C2, Cn are uniquely determined, so T alpha will also be uniquely determined, and hence we can say that T alpha is determined by T alpha 1, T alpha 2 and T alpha n. Now, we will introduce more concepts. To start with, the image T of linear transformation T from V to W is defined as the set consisting of all W's such that TV is equal to W for some V belonging to V. Sometimes this is also called as range of T. The kernel T of transformation T is defined as the set consisting of all vectors V in V such that TV is equal to identity in W. That way we define two sets, image T or range T and kernel T. So, these two sets are related with the linear transformation T. Clearly, image T is a subset of W and kernel T is a subset of V. In fact, we will prove that image T is a subspace of W, W being the vector space, kernel T is a subspace of V. Now, let us show it pictorially. We have two vector spaces V and W, X belongs to V, and under this transformation T, this vector X will go to Y. Now, this is the image set which is consisting of all Y's which has some point X in the set V. So, Y is an image of X. So, all these Y's include the range or image set which is contained in W. Now, for the kernel T, this is the domain in which the vectors will map to the identity vector theta in W. So, all these vectors in this domain will map to theta. So, kernel T is the set of all x in V such that Tx is equal to theta. So, this is a subset of V and this is a subset of W. Now, we say that a linear transformation T is said to be 1 1 if alpha not equal to beta belonging to V implies that T alpha and T beta, they are not the same. That means, if we have two different elements in V, then their images cannot be the same, they have to be different. That is, if T is 1 1, then if T alpha is equal to T beta, then alpha and beta have to be the same. A linear transformation T is said to be onto when range of T is equal to W. And another definition, if V T, the linear transformation from V into W, is an isomorphism if it is 1 1 onto. The vector space V and W are said to be isomorphic if there is an isomorphism of V into W. Now, again we show it here. We have two different elements, two different vectors in V, they map to different vectors in W. So, X maps to Tx and Y maps to Ty. If this is true for any combination of X and Y in V, then we say that the linear transformation is 1 1. In another example, here we have two X and Y in V, but both map to same element in W, that is X and Y are different in V, but they are same in W, and that means this transformation T is not 1 1. Now, in this case we have a vector space V and a vector space W. T is a linear transformation. X maps to this element Tx in W, Y maps to this element Ty in W, and this is the set in which we will have images in which the elements in V will map to this set. That means, if this set and the set W, they have become the same, then it becomes an onto transformation. That means, there is no element in this W which is not an image of this. Every element here is an image, is image of some point in V. That is onto transformation. Now we can prove these theorems, that consider linear transformation T, then image T is a subspace of W and kernel T is a subspace of W, a subspace of V. So, image T is a subspace of W and kernel T is a subspace of V. Now, first we prove the first result, that image T is a subspace of W. So, to prove this, we consider alpha beta belonging to image T. Then if C alpha plus beta also belongs to image T, then image T is a subspace. This is a very definition of subspace. So, we consider alpha and beta belonging to image T. So, Since they belong to image T, that means there must be some V1 in the set V, so that alpha is equal to TV1 and some V2 in V, so that beta is equal to TV2. So, let us consider alpha and beta in this way. So, C alpha plus beta is equal to C of T V1 plus T of V2, and since T is a linear transformation, so C alpha plus beta is equal to T of C V1 plus V2. Now, V is a subspace, therefore, CV1 plus V2 will also belongs to V. Let us call this vector as V3. Then C alpha plus beta is equal to T of V3. That means C alpha plus B is an image of V3, and that means C alpha plus beta also belongs to image T, and this proves that image T is a subspace. And the second part of the theorem is that kernel T is a subspace of V. So, we consider two vectors in kernel T, V1 and V2, and will prove that C1 V1 plus V2 is also in kernel T. That is the definition of subspace. So, we start with V1 V2 belonging to kernel T. Since they belong to kernel T, this implies that TV1 is equal to identity theta and TV2 is equal to theta. Now, since T is a linear transformation, then T of C1 V1 plus V2 is equal to C1 TV1 plus TV2, and that means T of C1 V1 plus V2 is also theta, and this proves that C1 V1 plus V2 also belongs to kernel T, and that is kernel T is a subspace. Now, there is a remark that kernel T is never empty, because T of theta is equal to theta. So, there is always a vector theta in kernel T which will map to theta itself. So, kernel T will never empty. Theta will always belong to kernel T. There may be more members in kernel T, but theta will always be in kernel T and it is never empty. Then second remark is, if kernel T is theta only, then dimension of kernel T is equal to 0. This is another remark. Then we have an important result regarding dimension of kernel T and dimension of image T or range T, and it says that if T is a linear transformation from V into W, then dimension of V is equal to dimension of kernel T plus dimension of image T. Now, to prove this result, we prove it in two different cases. The first case is that T is a 0 transformation. So, if T is a 0 transformation, then alpha belongs to V implies that T alpha is equal to theta, and kernel T in that case will be V, and image T will be theta itself, and dimension of image T in that case will be 0, or dimension of kernel T is equal to dimension of V is equal to n. So, dimension of V is equal to dimension of kernel T plus dimension of image T. So, that we have proved the first part when T is a 0 linear transformation. The second case is the dimension of kernel T is k, which is not 0. Now, to prove this, we have to prove that dimension of image T is n minus k. For this, let us say the basis for kernel T is alpha 1, alpha 2, alpha k, and kernel T being a subspace of V, we can prove that we have to prove that image T is equal to alpha k plus 1 alpha n. So, this is what we are going to prove. So, image T is actually generated by this set. So, basis for V is, let us consider it to be alpha 1, alpha 2, alpha k plus 1 alpha n. So, we have n dimensional vector space V, and the basis alpha 1, alpha 2, alpha k. This is the basis for kernel T being the subspace of V, and we have some additional vectors. So, basis for V is this. Let us consider beta belonging to image T, then there must be some alpha in V, so that beta is equal to T of alpha. So, we write down this alpha as a linear combination of the vectors of basis of V, that is alpha is equal to C1 alpha 1 plus C2 alpha 2 plus Cn alpha n. Then beta is equal to T of this vector. So, I write down this vector as C1 alpha 1 plus C2 alpha 2 plus Ck alpha k plus Ck plus 1 alpha k plus 1 up to Cn alpha n. So, that means I have divided this into two parts. This is the vector C1 alpha 1 plus C2 alpha 2 plus Ck alpha k is a linear combination of vectors alpha 1 to alpha k. That means this will belong to kernel T, and this will map to 0. So, I will use the property of linear transformation, and I write down beta as C1 T alpha 1 plus C2 T alpha 2 plus Ck T alpha k on one side, and Ck plus 1 T alpha k plus 1 plus up to Cn T alpha n as the second term. So, I have two terms. I have represented beta as sum of two terms, this term and this term, and that means beta is equal to T of C1 alpha 1 plus C2 alpha 2 plus Ck alpha k plus the second term, and this is a kernel T is a subspace, and therefore, C1 alpha 1 plus C2 alpha 2 plus Ck alpha k belongs to kernel T, and that is why T of this is equal to theta. So, this means beta is equal to simply this term. So, beta is equal to Ck plus 1 Tk alpha k plus 1 plus the last term is Cn T alpha n. Now, every vector in image T is spanned by this set, but we have to say that if these vectors are linearly independent, then we have proved the result. So, we have just said that any vector beta is a linear combination of T alpha k plus 1 up to alpha n. So, it is spanned by this set. What we have to see that they are linearly independent, and in that case B1 is a basis for image T. So, to prove this, let us consider D1 Tk plus 1 plus D2 T of alpha k plus 2 Dn minus k T alpha n is equal to theta. So, this linear combination of n minus k vectors is 0. Now, if this is 0, then T of D1 alpha k plus 1 is a linear property satisfied. So, T of D1 alpha k plus 1 plus D2 alpha k plus 2 plus Dn minus k alpha n is equal to 0. This is equal to T times I have added C1 alpha 1 plus C2 alpha 2 plus Ck alpha k. I have added this in this because it is 0 vector. This is mapping to 0. So, T of this is 0. So, I have added this into this term. So, since B is a basis, so C1 alpha 1 plus C2 alpha 2 plus Ck alpha k plus D1 alpha k plus 1 rest of the terms is equal to 0. And since it is a basis, so this linear combination is 0, means all the scalar terms C1, C2, Ck, D1, D2, D etc. are 0. So, C1, C2 etc. they are all identically 0, and that means alpha k plus 1, alpha k plus 2, alpha n are linearly independent, because these are 0. So, these vectors are linear, these vectors are linearly independent, and that means the dimension of image T is n minus k, because we are having n minus k vectors. So, what we have is dimension of image T plus dimension of kernel T is dimension of V. So, we have proved an important result. For the linear transformation T, rank of T is defined to be the dimension of image T. This is the definition, that rank of T is defined to be the dimension of image T, or rank of T is dimension image T. Similarly, nullity of T is defined to be the dimension of kernel T. So, nullity T is dimension of kernel T, and in this light we can say that rank of T plus nullity of T is equal to dimension of V. So, this is an important result and we will be using this at number of places. Now, another result, a linear transformation is 1-to-1 if and only if kernel T is equal to identity. We have only one element in kernel T, that is identity. Such a transformation is 1-to-1. Now, to prove this, we have to prove two parts. One is that T is 1-to-1, then kernel T is equal to theta, and the other part is if kernel T is equal to theta, then T is 1-to-1. So, let alpha belongs to V such that T alpha is theta. Also, T theta is theta, because theta will map to theta itself. This we have proved earlier. So, we have one more alpha which will take which this transformation T will take to theta. Now, this is 1-1 mapping. So, alpha has to be theta, no two different elements will go to same element theta in W. So, kernel T has to be theta. So, by contradiction we have proved that kernel T is equal to theta. So, this part is proved. The second is if kernel T is equal to theta, then T will be 1-to-1. Now, to prove this result, we consider alpha 1 and alpha 2 belonging to V such that T alpha 1 is equal to T of alpha 2. Then T of alpha 1 minus T alpha 2 is equal to theta, and since it is a linear transformation, T of alpha 1 minus alpha 2 is equal to theta, but alpha 1 minus alpha 2 will also belong to V because V is a subspace. So, the linear combination will also belong to V. So, T of alpha 1 minus alpha 2 is equal to theta, but we have said that only theta can map to this. So, kernel T is equal to theta. So, that means alpha 1 minus alpha 2 is equal to theta, and that proves alpha 1 is equal to alpha 2. So, this means T is 1-1. So, even if we have started with two different values, it comes out to be that these two vectors are the same, and this proves that T is 1-to-1. So, we have proved the result. Now, I will take some examples. The first example says that a transformation being given to us from R3 to R2, T A B C is equal to a vector in R2, A plus 2B plus C being the first component and minus A plus 3B plus C as the second component. Now, this linear transformation is being given to us. You have to find kernel T and its basis and dimension. So, we will start with the definition of kernel T. If T A B C is equal to theta, then A B C will belong to kernel T. This kernel T will be a member of R3. So, that is why I have considered 3-dimensional vector A B C. So, T of A B C will be 0, then A B C will belong to kernel T. Now, to prove this, we have to say that A plus 2B plus C is equal to 0 minus A plus 3B plus C equal to 0. This is to be there. This is because kernel T will be theta only. So, the first component has to be 0 and the second component has to be 0. So, if you simplify, then C is equal to minus 5k and B is equal to 2k. You can add the two and we will get this result. That means kernel T is equal to, the A is k, B is equal to 2k and C is equal to minus 5k, k belonging to R. That means any vector of this form will satisfy these equations. So, this vector will belong to kernel T. So, basis of kernel T will be 1, 2, minus 5. Any vector of this form can be generated from this. So, this is the basis for kernel T. So, kernel T will be having vectors of this form which will be generated by this vector. So, this forms a basis of kernel T, and since kernel T involves a vector of this form, so we say that this is the basis having only one vector. So, the dimension of kernel T is 1. Now, we will make use of rank T and nullity theorem. It says that rank T plus nullity T is equal to dimension V. Dimension V is given to be 3. Rank nullity is given to be 1. So, rank T is equal to dimension image T is equal to 3 minus 1 is equal to 2. So, dimension of image T is 2. In the second example, we consider a standard basis for R3 being E1, E2, E3, and we consider linear transformation from R3 to R3 defined in this manner. E1 will map to E1 plus E2, T of E2 will map to E3 plus 2E2, and T of E3 will map to E1 minus E2 minus E3. Now, this is the linear transformation is from R3 to R3. In my earlier result, I have proved that if you know how these elements are being mapped, you define the mapping and the mapping can easily be determined. So, we define the mapping in terms of mapping of E1, E2 and E3. So, this defines a mapping. Now, you have to show that the vectors T1, T2 and T3 are not linearly independent. So, let us consider V1 as T of E1, which is E1 plus E2, and V2 is TE2, which is E3 plus 2E2 being defined here. V3 is TE3 as E1 minus E2 minus E3. These are 3 vectors in R3. Let us consider the linear combination of these 3 vectors, that is C1 TE1 plus C2 TE2 plus C3 TE3 as 0. If these 3 vectors are linearly independent, then C1, C2, C3 will come out to be 0. Now, we use the definition of TE1, TE2, TE3 being given to us. So, we write down C1 E1 plus E2 as TE1 plus C2 TE2 as E3 plus 2E3 plus C3 times TE3 as E1 minus E2 minus E3 0. We will combine the different terms. We will have C1 plus C3 multiplied by E1 plus C1 plus 2C2 minus C3 multiplied by E2 plus C2 minus C3 multiplied by E3, and this is equal to 0. Since E1, E2, E3 are linearly independent, therefore, C1 plus C3 is equal to 0. C1 plus 2C2 minus C3 equal to 0. This is the coefficient of E2, and coefficient of E3 is C2 minus C3 equal to 0. Now, we have 3 equations to solve C1, C2 and C3. From the first equation, C1 is equal to minus C3, and from second, C2 is equal to C3. So, if you substitute C1 plus C3 is equal to 0 here, then we will have C1 plus C2 equal to 0, and that means C1 is equal to minus k, C2 is equal to k and C3 is equal to k is a possible solution for this, and k need not be 0. So, we have obtained a solution for this equation which is a non-zero solution, and that means TE1, TE2, TE3 are linearly dependent, they cannot be linearly independent because we have got this non-zero solution. Now, we can put a remark here. The set of linearly independent vectors may have linearly dependent images under a linear transformation. So, this is what has happened in the earlier example. We have started with a linearly independent set of vectors E1, E2, E3. We have a linear transformation T, but what we have T of E1, T of E2, T of E3, they are not linearly dependent, they are not linearly independent, but they are linearly dependent. And that is, the set of linearly independent vectors may have linearly dependent image under a linear transformation. Now, this is a theorem which says that if we have a linear transformation U into V, if it is 1-1 linear transformation, then the set of vectors u1, u2, un belonging to U are linearly independent vectors, then its images tu1, tu2, tun are also linearly independent vectors. So, basically this theorem provides a condition under which linearly independent vectors will map to linearly independent vectors, and the result is that the transformation has to be 1 1. So, here is the proof. We can start with a linear combination of vectors tu1, tu2, tun, and since T is a linear transformation, so we will have T of C1 u1 plus C2 u2 plus Cn un equal to 0, and U will belong to U because U is a vector space, the linear combination will also belong to U. Now, T is 1 1 or kernel T is equal to 0. So, we have been given that T is 1 1 transformation, and we have earlier proved that kernel T is equal to 0 if T is 1 1. That means T of U is equal to 0. So, this vector U has to be 0 because kernel T is equal to 0, and that means C1 U1 plus C2 U2 plus Cn Un is equal to 0, but we have U1 U2 Un has to be 0, that means C1 C2 Cn has to be 0. So, that means we have a linear combination which is 0 and these coefficients comes out to be 0, and that means tu1, tu2, tun are linearly independent. So, under this condition we will have a linear vectors will go to linear independent vectors will go to linearly independent set of vectors. Now, what happened in the earlier example, which was Te1 is equal to E1 plus E2, Te2 was E3 plus 2E2, Te3 is E1 minus E2 minus E3. In this example, the vector E1 minus E2 minus E3 is actually linear combination as Te1 minus Te2 minus Te3, and this is actually 0, and that means the vector E1 minus E2 minus E3 belongs to n of t, and dimension of nt is equal to 1 in that case. So, according to rank nullity theorem, the rank of t is dimension of image t, which is 2, and in this case they are actually not mapping to, the 3 vectors cannot be linearly independent. Now, I have one more simple result, that if I have a linear transformation from R4 to R6, the linear transformation, and if dimension of kernel T is given to be 2, then dimension of range of T or image of T can be computed as 4 minus 2, it is 2. You have to make it clear that the dimension of V is to be considered in rank nullity theorem, not the dimension of W. So, the result here is 2. Similarly, if dimension of range T is 3, then dimension of kernel T is 1. So, 3 plus 1 is equal to 4. So, this rank and nullity theorem can be used to obtain the dimension of kernel T. If other two things are given, can be obtained for dimension of range T if dimension of V is given and dimension of kernel being given to us. Viewers, with this we have come to the end of this lecture. To summarize what we have done today, I have started with the definition of linear transformation. I have given some examples. I have illustrated with the help of examples what do we mean by linear transformation, what do we mean by additive property, what do we mean by homogeneous property. And then we have discussed several results related with linear transformations. I have introduced the concept of kernel and nullity, and we have finally established a theorem relating range, dimension of range and dimension of kernel with the dimension of the vector space V. We will continue with this, we will discuss more concepts related to this in my next lecture. Thank you.
Thank you.